Bro, have you watched yesterday's match?
Yes, bro. It was a nice match. Glad I completed my studies earlier, so I didn't miss the greatest match in the history of IPL.
Bro, I could not understand the chapter, alcohols, phenol, and ether, so I skipped the studies yesterday.
Bro, it's very easy chapter.
Your team owner runs an alcoholic brand. I think that's the reason you understand this chapter very well.
In 2016 and 2017, you skipped the Indian Premier League. Now skipping the lesson. When will this habit go from you?
Bro, stop trolling, and if you can teach it to me.
Apart from the Royal Challenge alcohol you mentioned earlier, there are a lot of other uses to these alcohols, phenols, and ethers. There will be no notebooks, newspapers, currency notes, checks, certificates, etc. Even in cricket, you can't make tifos, banners, or the captains even can't submit the team sheet before the toss. It would have been a really different world. An alcohol contains one or more hydroxyl group directly attached to carbon atoms of an aliphatic system, while a phenol contains OH groups directly attached to carbon atom of an aromatic system. The substitution of a hydrogen atom in a hydrocarbon by an alkoxyl or aryloxyl group yields another class of compounds known as ethers. You may also visualize ethers as compounds formed by substituting the hydrogen atom of hydroxyl group of an alcohol or phenol by alkyl or aryl group. The classification of compounds makes their study systematic and hence simpler. Alcohols and phenols can be classified based on how many hydroxyl group they have. If they have one hydroxyl group, they are called as monohydric. If they have two hydroxyl group, they are called as dihydric. If they have three hydroxyl group, they are called as trihydric. If they have many hydroxyl group, they are called as polyhydric. Monohydric alcohols may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. In compounds containing sp3 carbon-oxygen bonds, the OH group is attached to an sp3 hybridized carbon atom of an alkyl group. They are further classified into primary alcohols where the OH group is attached to a primary carbon. Secondary alcohols where the OH group is attached to a secondary carbon. Tertiary alcohols where the OH group is attached to a tertiary carbon. Allylic alcohols where the hydroxyl group is attached to a sp3 hybridized carbon that is next to an carbon-carbon double bond. In compounds with sp2 hybridized carbon atom, the hydroxyl group bonded to a carbon-carbon double bond are vinylic alcohols. Ethers are also classified as simple or mixed. If both groups attached to the oxygen are the same, they are called as simple or symmetrical. Diethyl ether is an example for this. If the two groups are different, they are called as mixed or unsymmetric. Ethyl methyl ether and phenyl ethyl ether are some examples of this.
Okay, bro. I always find it difficult to understand the nomenclature. And can you explain the difference between common names and IUPAC names?
So, I will explain this with an example of the uncapped wicketkeeper of your team. What is he commonly called?
Thala or MSD?
Okay, now what is his official name?
Mahendra Singh Dhoni.
Just like how you call him as Tala or MSD, the compounds also have some common names and these are called as common names of the compound. The common name of an alcohol is derived from the common name of the alkyl groups and adding the word alcohol to it. For example, CH3OH is methyl alcohol. Common names of either are derived from the names of alkyl or aryl groups written as separate words in alphabetical order and adding the word either at the end. For example, CH3O C2H5 is ethyl methyl ether. If the alkyl groups are the same, the prefix di is added before the alkyl group. For example, C2H5O C2H5 is diethyl ether. Mahendra Singh Dhoni is his official name. Similarly, there are some official names given to the compounds and these are called as IUPAC names. According to IUPAC system, the name of an alcohol is derived from the name of the alkane from which the alcohol is derived by substituting E of alkane with the suffix OL. The position of substituents are indicated by numerals. According to IUPAC system of nomenclature, ethers are regarded as hydrocarbon derivatives in which a hydrogen atom is replaced by an OR or OAR group, where R represent alkyl and AR represent aryl groups. The larger alkyl groups is chosen as the parent hydrocarbon.
Bro, next explain me the thing in which your brand is expert in. I mean, preparation of alcohols.
I know your team doesn't prepare for anything, so I will explain how to prepare to you. Alcohols can be prepared from alkenes, carbonyl compounds like aldehyde and ketones, carboxyl acid or esters, and Grignard reagents. From alkenes, it is prepared either by acid catalyzed hydration or by hydroboration oxidation. In acid catalyzed hydration, alkanes react with water in presence of an acid to form alcohols. This method follows Markovnikov's rule, which means that when water adds to an alkene, the hydrogen atom attached to the carbon with the most hydrogen atoms. This occurs in 3 steps. In first step, the alkanes get a hydrogen ion from the acid, creating a positively charged carbocation. It is called as protonation. In step 2, water acting as nucleophile attacks the carbocation, and this step is called as nucleophilic attack. In step 3, a hydrogen ion is removed, resulting in the formation of an alcohol. In hydroboration oxidation, diborane react with alkene to give trialkyl boranes as addition product. This is oxidized to alcohols by hydrogen peroxide in the presence of aqueous sodium hydroxide. The addition of borane to the double bond takes place in such a manner that the boron atom gets attached to the sp2 carbon carrying greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by addition of water to the alkene in a way opposite to the Markovnikov's rule. From carbonyl compounds, it is formed by reduction of aldehydes and ketones and by reduction of carboxyl acids and esters. In reduction of aldehydes and ketones are reduced to the corresponding alcohols by addition of hydrogen in the presence of catalyst. The usual catalyst is a finely divided metal such as platinum, palladium or nickel. It is also prepared by treating aldehydes and ketones with sodium borohydride or lithium aluminum hydrate. Aldehydes yield primary alcohol, whereas ketone gives secondary alcohols. In reduction of carboxylic acid and esters, the carboxylic acids are reduced to primary alcohol in excellent yield by lithium aluminum hydride, which is a strong reducing agent. However, lithium aluminum hydride is an expensive reagent and therefore used for preparing special chemicals only. Alcohols are also produced by the reaction of Grignard reagent with aldehydes and ketones. The first step of the reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Hydrolysis of adduct yields an alcohol. The reaction produces a primary alcohol with methanol, a secondary alcohol with other aldehydes and tertiary alcohols with ketones. Phenols, also known as carbolic acid, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically. In the laboratory, phenols are prepared from benzene derivative by any of the following methods. First is from haloarenes, where chlorobenzene is fused with sodium hydroxide at 623 Kelvin and 320 atmospheric pressure. Sodium phenoxide formed as a resultant is then acidified to obtain phenol. Second is from benzene sulfonic acid, where benzene is sulfonated with oleum to form benzene sulfonic acid. It is then converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of sodium salt gives phenol. Third is from disonium salt, where a disonium salt is formed by treating an aromatic primary amine with nitrous acid at 273 to 278 Kelvin. These disonium salts are then hydrolyzed to phenols by warming with water or by treating with dilute acids. The last one is from cumin, where cumin, which is also called as isopropyl benzene, is oxidized in the presence of air to cumin hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Most of the worldwide production of phenol is from cumin. Ethers are prepared either by dehydration of alcohols or through Williamson ether synthesis. In dehydration of alcohols, alcohols undergo acid catalyzed dehydration when treated with strong protic acids like sulfuric acid or phosphoric acid, producing either alkenes or ethers depending on reaction conditions. The key factors are temperature and the type of alcohol, that is primary, secondary or tertiary. At high temperature, about 170 degrees Celsius, the reaction favors elimination, forming an alkene. For example, ethanol dehydrates to ethene when heated with concentrated H2SO4. Secondary and tertiary alcohols especially favors this pathway since they form stable carbocations, making elimination easier. At lower temperatures, about 140 degrees Celsius, substitution, especially SN2, dominates, leading to ether formation. Here, one alcohol molecule attacks another, forming a COC bond. For instance, ethanols yield ethoxyethane under these conditions. However, this works best with primary alcohols because their unhindered structure allows the SN2 mechanism. Secondary and tertiary alcohols rarely form ethers because their bulky groups hinder nucleophilic attacks. Elimination is much faster. Thus, ether synthesis is only practical for simple primary alcohols at controlled temperature, while higher temperature or more substituted alcohols lead to alkenes. This balance between substitution and elimination defines the outcome of alcohol dehydration. Williamson synthesis is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with sodium alkoxide. The reaction involves SN2 attack of an alkoxide ion on primary alkyl halide. Better results are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halides, elimination competes over substitution. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, the reaction of CH3ONA with CH3 thrice CBr gives 2-methylpropane. It is because alkoxide are not only nucleophiles but strong bases as well. They react with alkyl halides leading to elimination reactions. Phenols are also converted to ether by this method. In this, phenol is used as the phenoxide moiety.
Bro, can you now tell me about their physical properties?
The boiling points of alcohols and phenols increase with increase in the number of carbon atoms due to increase in van der Waals forces. In alcohols, the boiling point decreases with increase of branching in carbon chain because of decrease in van der Waals forces with decrease in surface area. The hydroxyl group in alcohols and phenols is involved in intermolecular hydrogen bonding. It is interesting to note that boiling points of alcohols and phenols are higher in comparison to other classes of compound, namely hydrocarbons, ethers, haloalkanes and haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses but their boiling point differ widely. The boiling points of methoxymethane is intermediate of the two boiling points. The high boiling points of alcohols are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ethers and hydrocarbons. The carbon-oxygen bond in ethers are polar and thus ethers have a net dipole moment. The weak polarity of ethers do not appreciably affect their boiling points, which are comparable to those of alkenes of comparable molecular masses but are much lower than the boiling points of alcohols. Alcohols and phenols are water soluble due to hydrogen bonding between their hydroxyl groups and water molecules. Lower molecular weight alcohols like methanol and ethanol exhibit complete miscibility with water. Solubility decreases with increasing hydrocarbon chain length as the hydrophobic alkyl or aryl component dominates over the hydrophilic OH. The miscibility of ethers with water resembles those of alcohols of the same molecular mass because just like alcohols, oxygen of ether can also form hydrogen bonds with water molecules. Alcohols are versatile compounds. Just like how KL Rahul plays at any position, they react both as nucleophiles and electrophiles. The bond between OH is broken when alcohols react as nucleophile, and the bond between carbon and oxygen is broken when they react as electrophiles. Based on the cleavage of oxygen hydrogen and carbon oxygen bonds, the reaction of alcohols and phenols may be divided into two groups, that is, one in which reaction involves cleavage of OH bond and the other reaction involving cleavage of carbon oxygen bond. Alcohols and phenols react with active metals such as sodium, potassium and aluminum to yield corresponding alkoxide or phenoxide and oxygen. In addition to this, phenols react with aqueous sodium hydroxide to form sodium phenoxide. These reactions show that alcohols and phenols are acidic in nature. In fact, alcohols and phenols are bronzed acid, that is, they can donate a proton to a stronger base. Alcohols can act as weak acid because their OH bond can break to release H plus ions. The next topic is acidity of phenol, where the reaction of phenol with methyl and sodium hydroxide indicate its acidic nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which acts as an electron withdrawing group. Due to this, the charge distribution in phenol molecule causes the oxygen of OH group to be positive. The reaction of phenol with aqueous sodium hydroxide indicates that phenols are stronger acid than alcohols and water. Due to the higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decreases on oxygen. This increases the polarity of OH bond and increases the ionization of phenols than that of alcohols. In alkoxide ion, the negative charge is localized on oxygen, while in phenoxide ion, the charge is delocalized. The delocalization of negative charge makes phenoxide ion more stable and favors the ionization of phenol. Although there is also charge delocalization in phenol, its resonance structure has charge separation due to which phenol molecule is less stable than phenoxide ion. Electron withdrawing group like NO2 at ortho or para position increase phenol's acidity by stabilizing the phenoxide ion's negative charge. Electron donating groups like CH3 reduce acidity by destabilizing the phenoxide ion. Thus, nitrophenols are stronger acid than phenols, while cresols are weaker acids. Esterification also comes under reaction involving oxygen-hydrogen bond. Here, alcohols and phenols react with carboxyl acid, acid chlorides and acid anhydrates to form esters. The reaction with carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible and therefore water is removed as soon as it is formed. The reaction with acid chloride is carried out in the presence of a base called pyridine so as to neutralize hydrochloric acid, which is formed during the reaction. It shifts equilibrium to the right hand side. The introduction of acetyl group in alcohols or phenol is known as acetylation. Acetylation of salicylic acid produces aspirin. There are 5 main reactions which comes under reaction involving carbon-oxygen bond in alcohol. First is reaction with hydrogen halides. Here alcohols react with hydrogen halides to form alkyl halides. This becomes one of the most important reactions because Lucas test comes under this reaction. The Lucas test distinguishes primary, secondary and tertiary alcohols by their reaction rates with hydrochloric acid or zinc chloride. Tertiary alcohols react instantly, causing intermediate turbidity as insoluble alkyl chlorides form. Secondary alcohols take 5 to 10 minutes to cloud the solution, while primary alcohols remain clear at room temperature. Second is reaction with phosphorus trihalide, where alcohols are converted to alkyl bromides by reaction with phosphorus tribromide. Third is dehydration, where alcohols undergo dehydration to form alkene on treating with protic acid such as concentrated sulfuric acid or phosphoric acid, or catalysts such as anhydrous zinc chloride or alumina. For example, ethanol undergoes dehydration by heating it with concentrated sulfuric acid at 443 Kelvin. The mechanism of this reaction involves three steps. Step 1 is formation of protonated alcohol. Step 2 is formation of carbocation. It is the slowest step and hence the rate determining step of the reaction. Step 3 is the formation of ethene by elimination of a proton. Fourth is oxidation. Oxidation of alcohols involves formation of carbon-oxygen double bond with cleavage of an OH and CH bonds. These are also known as dehydrogenation reaction as these involve loss of dihydrogen from an alcohol molecule. Depending on oxidizing agent used, a primary alcohol is oxidized to an aldehyde which in turn is oxidized to carboxylic acid. Strong oxidizing agents such as acidified potassium permanganate are used for getting carboxylic acid from alcohols directly. Chromium oxide in anhydrous medium is used as oxidizing agent for isolation of aldehydes. Now let's see some reactions which are only shown by phenols. First is electrophilic aromatic substitution in phenols. In phenols, the hydroxyl group makes the benzene ring more reactive and attracts new group to the ortho and para position because these spots become electron rich due to hydroxyl group's influence. Common electrophilic aromatic substitution reaction taking place in phenols are as follows. First is nitration and second is halogenation. In nitration, dilute nitric acid at low temperature react with phenol to yield a mixture of ortho and para nitrophenols. The ortho and para isomers can be separated by steam distillation. Ortho nitrophenol is steam volatile due to intramolecular hydrogen bonding, while para nitrophenol is less volatile due to intermolecular hydrogen bonding. Phenol reacts with concentrated nitric acid to form 2,4,6 trinitrophenol, which is commonly known as picric acid. In halogenation, phenol is treated with bromine at different conditions to form different products. When phenol reacts with bromine in nonpolar solvents like trichloromethane or CS2 at low temperature, it forms monobromophenol. No Lewis acid is needed because the hydroxyl group activates the ring, helping bromine react directly. When phenol reacts with bromine water, it forms 2,4,6 tribromophenol. In this reaction, a white solid precipitates out instantly due to high reactivity from the OH group. Second one is Kolb's reaction, where phenol is treated with sodium hydroxide to form phenoxide ion, which is even more reactive than phenol towards electrophilic aromatic substitution. Hence, it undergoes electrophilic substitution with carbon dioxide and forms orthohydroxybenzoic acid. Third is Reimer-Tiemann reaction, where phenol is treated with chloroform in presence of sodium hydroxide. As a result, a aldehyde group is introduced at the ortho position of benzene ring. Then the substituted benzyl chloride is hydrolyzed in the presence of alkali to produce salicyl aldehyde. Fourth one is reaction of phenol with zinc dust, where phenol is converted to benzene on heating with zinc dust. Fifth one is oxidation, where phenol is oxidized with chromic acid to produce a conjugated diketone known as benzoquinone. In the presence of air, phenols are slowly oxidized to dark colored mixtures containing quinones. Ethers are the least reactive of the functional groups. The cleavage of carbon-oxygen bond in ethers takes place under drastic conditions with excess of hydrogen halide. The reaction of dialkyl ethers gives two alkyl halide molecules. Alkyl aryl ethers are cleaved at the alkyl oxygen bond due to the more stable aryl oxygen bond. The reaction yields phenols and alkyl halides. Ethers with two different alkyl groups are also cleaved in the same manner. However, when one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. In case of anisole, methylphenyl oxonium ion is formed by protonation of ether. The bond between oxygen and methane is weaker than the bond between the oxygen and the phenyl. Because of the carbon of the phenyl group is sp2 hybridized and there is a partial double bond character. Therefore, the attack by iodine ion breaks oxygen methane bond to form iodomethane. Phenols do not react further to give halide because sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conversion to halide. Now let's see three important electrophilic substitution reaction in ethers. First is halogenation, where phenyl alkyl ethers undergo usual halogenation in the benzene ring. For example, anisole undergoes bromination with bromine in ethanoic acid and yields para-bromoanisole as major product and ortho-bromoanisole as minor product. Second one is Friedel-Crafts reaction. In this reaction, the alkyl and acyl groups are introduced at the ortho and para positions by reaction with alkyl halides and acyl halides in the presence of anhydrous aluminum chloride as catalyst. Third is nitration, where anisole reacts with a mixture of concentrated sulfuric and nitric acid to yield a mixture of ortho and para nitroanisole.
Can you tell me about some commercially important alcohols?
Methanol and ethanol are among the two commercially important alcohols. Methanol, also known as wood spirit, was produced by destructive distillation of water. Today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature. Methanol is a colorless liquid and boils at 337 Kelvin. It is highly poisonous in nature. Ingestion of even small quantities of methanol can cause blindness and large quantities cause even death. Methanol is used as solvent in paints, varnishes and chiefly for making formaldehyde. Ethanol is obtained commercially by fermentation. The sugar in sugarcane or fruits such as grapes is converted to glucose and fructose in the presence of an enzyme invertase. Glucose and fructose undergo fermentation in the presence of another enzyme, zymase, which is found in yeast. In winemaking, grapes are the source of sugars and yeast. As grapes ripen, the quantity of sugar increases and yeast grows on the outer skin. When grapes are crushed, sugar and the enzyme comes in contact and fermentation starts. Fermentation takes place in anaerobic condition, that is in absence of air. Carbon dioxide is released during fermentation. The action of zymase is inhibited once the percentage of alcohols formed exceeds 14%. If air gets into fermentation mixture, the oxygen of air oxidizes ethanol to ethanoic acid, which in turn destroys the taste of alcoholic drinks. Ethanol is a colorless liquid with boiling point 351 Kelvin. It is used as a solvent in paint industry and in the preparation of a number of carbon compounds. The commercial alcohol is made unfit for drinking by mixing in it some copper sulfate to give it a color and pyridine for a foul smell liquid. It is known as denaturation of alcohols.
Bro, thanks for helping me. Have you noticed the irony? Even though you are a supporter of Royal Challengers Bengaluru, you helped me. But nowadays, these fan fights are getting toxic. Even some are ready to kill others.
Bro, that is what the broadcasters wanted. They wanted us to fight in the name of franchise and make money. Do you know one thing? Even BCCI is not a governmental organization. I will provide a link in description. See it and understand the reality. At least let us pledge to be not involved in a toxic fan fight.